Okay, hello everyone. Nice to see so many of you at our TaPaSCo tutorial. And yeah, I'd like to welcome you here to experience TaPaSCo with us for this day. First of all, before we get started, I just want to see what kind of people are here or what your experiences are. So I guess most of you have experience with FPGAs, I guess. Anyone who never touched an FPGA or has no idea what an FPGA is? That's very good. I guess most also use Xilinx. Anyone just with Altera experience? Okay, nice. So, any experience with HLS? I guess most of you, a lot of talks we already seen for those who attended the conference as well. And is there anyone from a totally different domain, not related to FPGAs, like network processing, databases, whatever? Okay. Okay. That's totally different. Nice. So we are quite homogeneous, and what we're going to do today is show you our tool TaPaSCo, Task Parallel Systems Programmer, System Composer. And we want to show you a bit what it does, how it does it, and you're going to experience it hands-on, yeah, to play around with it to get you started, hopefully. So first of all, before we start with the main part, I just wanted to introduce ourselves. So on the right, we have Carsten Heinz, the guy looking at his mobile phone. Then Lukas Sommer and myself, I'm Jaak Hofmann, and we are all PhD students at Andreas Koch's group. And Carsten and I are main developers of TaPaSCo right now. And Lukas is one user of TaPaSCo, so we have a bit of different experience. He submits a lot of issues in GitHub, and we have to fix it. So the other person who is of interest today is Yannick Lavan, who's here, and he's going to help you if you get stuck at some point during the tutorial. We as well, just to have one more hand to help us do things. So I guess most of you saw the talk yesterday. Just to give you a short overview again about what we're trying to do. We have TaPaSCo, which is a SoC generator for FPGA developers, or for targeting FPGAs, and you can just download it at GitHub. Here is the link in our own little group on GitHub. And the main focus is for a developer targeting FPGAs to be able to focus on developing the interesting part, the accelerators, and not having to deal with infrastructure over and over and over again. So we try to abstract away a lot of the hassle when it comes to dealing with the tools. What's the best practice to copy data over to the device, stuff like that. And we're trying to abstract that away from you. So what it does, in very short, is 4 parts. We generate bit streams for you for a multitude of different platforms. We help you find good configurations for a given platform, and most of this is automatic. We also do bitstream loading. Might not sound like a big deal, but I've experienced a lot of trouble sometimes with some kind of FPGAs getting it to load. And last but not least, we have a consistent FPGAs for all, consistent API for all platforms. So it doesn't matter if you target a sync device, some high performance ultra-escape loss vertex device. You can always use the same software. You just have to recompile it if it's a different architecture, of course, for the host processor. But apart from that, you don't have to change anything to run your code on the different devices or run the accelerators on different devices. Right now, we already have a lot of platforms supported, basically 2 classes right now. So we have the PCIe-based devices, which are mainly the Virtex UltraScape bus boards. Here are 2 examples, the 1525 and the Alveo boards for data centers, and the somewhat older Virtex 7-based VC709 and NetFPGA Zume. But those are just examples. We have a few more if you look at the repository later on. The other big group would be the sync-based device, so running on ARM hosts and connecting with AXI to the FPGA. And there we have support for the older sync-based Sync 7000, like ZC 706, and also the newer UltraScale Plus MPSoC-based systems like the ZCU 102. But those are just examples, and you can easily extend, especially in those families. So if you have a new Vertex 7 device, you basically have to add your constraints files, and that's it. Everything else is already handled by TaPaSCo, usually. Before we get started with like the main topic of this tutorial, I want to show you some examples of what we did or what other people already did with TaPaSCo, just to give you an idea, maybe give you a better understanding what you can do and what's the potential for you, especially as well for non-FPGA researchers, so people who usually don't touch hardware. One of the very interesting features we already saw in the talk yesterday is the design space exploration. So you have a given platform, especially with TaPaSCo, you have a wide variety of platforms with orders of magnitudes difference in resources and connectivity and so on. And usually it's not very intuitive to find the optimal configuration for a given FPGA, because there are trade-offs between sizes of the accelerator, for example, and frequencies runs, and it's not always the biggest device with the highest frequency. Well, this would be optimal, of course, but usually if you make it bigger, it runs slower and so on. So TaPaSCo can optimize for three things right now. So you can just optimize for area. So you have a given FPGA and you tell yourself, hey, I paid $5,000 for this, make it as full as possible. I want to use every last bit of silicon. You can optimize only for operating frequency. So TaPaSCo tries to find the maximum frequency a given accelerator runs on the given device. Or alternative implementations. So say you have 4 implementations of your accelerator, that those are a bit different. For example, one is a lot larger but faster per core, or you have a small accelerator which is smaller, slower per core, but you can put more of those on the FPGA. Those are the main operating modes, and you can combine these. So for example, if you run the command at the bottom, Pesco Explorer, then you give your core configuration. In this case, it's a semi-global block matching accelerator I wrote a few years back. And you tell TaPaSCo to find the optimal configuration in area and frequency. And then TaPaSCo heads out, does some heuristic approaches, of course. So we cannot guarantee it's a global optimum or anything, but we usually find a good result. And then TaPaSCo starts and heads out and tries to find, of course, the sweet spot between number of PEs, because if you go too high, you have some overhead from communications, for example. So not like the top left corner would be the best approach, but you might go somewhere here with less PEs, with a good frequency, and then you have your optimal configuration. To give you an example of that, where it worked quite well, as I said, I wrote this little semi-global block matching accelerator, and it was configurable. So you can change the number of parallelism mainly in the cores. And higher as a parameter means usually more hardware usage in this case. And I also did performance simulations. So I knew quite well how a given configuration would run on the FPGA. And what this algorithm does, for those who don't know it, you have a left and a right image from 2 cameras, and you basically extract the depth information, so how far a given pixel is away from the camera. It can be quite computative intensive task. But not to talk too much about the algorithm, I want to give you the results. So what TaPaSCo helped me. I just told it to go ahead and find the optimal configuration. And for the small devices, it pretty much did what everyone would expect. So the most interesting lines are here. So you have P and D, which are the 2 parameters. Larger means bigger cores, but also faster cores. And N means the number of replications of a given core. So for the small boards, like the Z board, well, it takes largest configuration basically with the highest frequency it could fit on the device. And then we have a heuristic here, the frames per second TaPaSCo expected, and yeah, well, for those devices they are rather deterministical, and we can predict it quite well for the given performance. So for the somewhat larger sync device, the ZC706, we have the same result. It just takes the biggest core it could find or fit on there with the highest frequency it could fit on there, and then we again, the heuristic is quite close to frames per second. But when we go to even larger devices, something interesting happens here. TaPaSCo goes out and says, okay, I could fit a much larger device on there, but then the frequency drops too low and I lose performance in the end. So what TaPaSCo does, or finds out here, we can take a smaller configuration. So as you can see, the configuration here is bigger than on the much larger device, but we just take 3 cores instead of 1. And from this, we get a much higher performance. And as you can see as well, the heuristic for PCI Express-based devices is still quite good, but yeah, as the communication overhead is a bit more difficult to predict, yeah, the heuristic is a bit far off. And as you can see for the other results, it changes quite a lot. For example, here for larger resolutions, which means larger buffers and so on, we have the predicted result here for the smaller device. The Z-board couldn't run it anymore, and for the VC709 again 2. But for the largest resolution, for example, it will also only do 1 big core on the largest device. Just to give you an idea about how TaPaSCo or what TaPaSCo can find for you in this area. Another area where you can see how well TaPaSCo can be extended, we have a plugin to support SFP Plus and QSFP based processing. Especially, I wrote this together, or I helped people from the P4 domain, so that's yeah, a language for network processing or for packet processing. And it's used, for example, in barefoot switches to process packets or to switch packets around. And they wanted to have higher performance, and they had a bit of a shim layer which worked on the NetFPGA Zume, but not on any other platforms. So I helped them. I integrated a little plugin into TaPaSCo, which made it possible for our processing elements to also process network streams. And we made this configurable. It's like 100 lines of in our case, TCL in this case for the plugin. And you can now use it on all the different platforms. You can add, well, if the platform has SFP Plus or QSFP caches, you can just say, here, I have this kernel, this processing element, and I want to connect it to some kind of Ethernet. And you can just simply yeah, do network processing. And one of the papers we used it in is this little ABD in the network. ABD is an algorithm for consensus, and you basically have some kind of clients, then you have a programmable switch, and cut off sadly, but on the right is basically intelligent memory directly connected to the network. And the programmable switch runs TaPaSCo basically, all the memories run TaPaSCo, and it was very easy to yeah, to get them up to speed that they can run Ethernet IP very easily. And what's also interesting, we didn't have like 20 NetFPGA Zume, but that didn't matter because I could just say, okay, we have a ZCU102, we take that, a VCU709, NetFPGA Zume, we just put them together. It's all the same host software, it's the same accelerator, and everything that's different between the platforms TaPaSCo handles. Another thing which we are currently working on, which is implemented in TaPaSCo, is support for softcore processes. We, for example, used it to evaluate different available RISC-V cores. We basically packaged the available RISC-V cores. You can just get on your GitHub or wherever. And we made it possible to put them on the FPGA through TaPaSCo. And right now we have a good selection. Most available RISC-V cores, at least that are compatible with TaPaSCo, we already packaged. And we took them and then we just put them through design space exploration, and we got nice graphs. And for example, this is the graph of the maximum frequency TaPaSCo found for these 4 different RISC-V or 3 RISC-V cores in the microplace, comparing them to each other in maximum frequency, which was basically just pressing a button telling TaPaSCo to go, and it found those frequencies. The same for the maximum number of PEs, so smaller cores versus larger cores. You could also do the same for performance data, so how many Triston MIPS per megahertz, for example. It was just telling TaPaSCo to go, then you put, we have capability to load your program, and then you go. Another thing which used the plugin system of TaPaSCo is the Heterogeneous System Architecture Integration. So HSA is mainly focused around ARM and AMD right now. They try to abstract heterogeneous architectures away, and we were adding FPGA into the mix, so you can use all the upper layers of which HSA provides, and run your stuff on the FPGA as well. And you can find the implementation there, and it basically uses TaPaSCo as a baseline. So we can support all the platforms TaPaSCo supports already. We can reuse a lot of existing infrastructure and only add the necessary infrastructure we have to add to support this HSA. A project which mainly Lucas, as I said, he's our main issues contributor to the project, and he's using it for his compiler work. So he's a compiler guy. He doesn't really like hardware, but still his compilers somehow produce hardware. And he used TaPaSCo as basically a runtime for his code. So he had a compiler which produced from some kind of input code. It produced, which is OpenMP, as you can guess. It's abstracted away all the hardware part and used the TaPaSCo API to integrate with the accelerator, generate the accelerators. So again, he has the advantage of all this hardware stuff is basically he doesn't have to care about. He can run it on different platforms. He can use our APIs or our kernel modules, and it just has to integrate it in the OpenMP runtime. So again, saving a lot of time instead of having to reinvent the wheel. Another thing he did is basically the same for machine learning, which is a DSL, I think, right? For machine learning generation. In these cases are, how were they called again? Some product networks, right? And he just produced the accelerators again in the format for TaPaSCo. He didn't have to know anything about how PCI Express works, how XAXI works. He just implemented those accelerators, and it worked. You can use DSE to find out the optimum frequency, the optimum size, and so on. Okay, that's enough for the basically advertisement slides, or to give you an idea about what we did with it or what we're still doing with it. Now we go on to give you the main terms I was using already before, like processing elements, just to give you an idea what we mean when we say processing elements. For those of you who saw the talk yesterday, it's a bit redundant, but just to give you a quick overview before we get started with the hands-on examples. So TaPaSCo a few years ago was founded as a thread pool composer. At some point we decided to rename it and have a nicer logo because thread pool composer doesn't look nice. And now we have these perfectly not copyright infringement logo. And it comes from Repara, which basically was targeted, or the project was targeted at simplifying the use of heterogeneous system architectures, not only FPGAs, but also GPUs and DSPs. And from this project, we took our part basically out of it, and we actively continued to develop it because we noticed, okay, this TaPaSCo stuff does really what we want to have. We don't want to reinvent the wheel again and again, and we want to, we found it really useful just for us as users ourselves because we develop accelerators and we are also actively using it. So starting with only the Vertex 7, VC709, and the sync board back at Threadpool Composer, we heavily extended it to all the series we saw before. So what are the main components of a TaPaSCo design? To give you an overview, we have a layered infrastructure which is quite flexible, but as a baseline doesn't require a lot of configuration from you. So what you have to do is provide an accelerator in the TaPaSCo compatible format, which is currently IPXAct. So for those of you who used Vivado before, most likely know this format, which is used for all the little building blocks in a design. And the other thing is you have to write your own software. So we provide an API, and later on you will play around with that, and you can just say, launch my accelerator with these kinds of parameters, and TaPaSCo will do the rest. Then we have basically two parts. So we have platform-specific part, which is of course the host FPGA interface, depending on the platform. The FPGA provided infrastructure, for example, how many memory banks do you have, what kind of memory do you have, just DDR RAM, or do you have some kind of flash, consistent memory, stuff like that. And some part of the driver. Most of the driver is platform independent, but of course, if you have a PCI Express device, that's initialized differently from a sync-based device. And then platform independent, we have some status providers, so TaPaSCo knows what the bit stream does, and there is some information about that, and also the processing element architecture, which we will see now. So what's a processing element? That's the thing you have to care about. That's the thing you provide. So in a very abstract way, it has this T-shape. You have control, which usually is Xe4 Lite for right now for the Xilinx-based devices, which is used to basically start your processing element, configure parameters, stuff like that. Then on the right side you have data, which currently is mostly Xe4 memory mapped, but as I showed before, with a plugin system we changed that to process streams, Ethernet streams, so that's also possible. It's just the baseline uses Xe4 memory mapped. And then at bottom, signaling could be anything really, but mostly what we are using here is an interrupt to signal if the processing element has finished. And then we go up the layers, so that's the thing you provide, and now you have to do some kind of configuration. You have to tell us how many of your processing elements you need, so you just tell TaPaSCo, my perfect kernel times 15, and then from those it will generate the processing cluster, which again has the same T-shape, just with the same semantics as before, and you have all those processing elements in there. And then we go up another layer, which looks almost the same, but we aggregate here different processing elements. So you can have a heterogeneous architecture on there with different kinds of processing elements. So one for algorithm A, one for algorithm B, and so on. And those are again clustered in these processing clusters in the architecture. And that's basically the platform independent part of a bit stream. And that's put into the platform dependent part, which is here in this greenish color. And you have the connections for the different parts. So for example, data aggregators usually are connected to DDR or some BRAM controllers or whatever you need. And on the left, the control aggregators are connected to the host through some way or another. And on the bottom, you have the interrupt handling, for example. So MSIX for PCI Express. So the software part is also layered, as you might imagine. We have a device driver, which is has a lot of common code for all the platforms, so for ARM and the PCI Express devices, which is here in this device driver column. And then, as I said before, a bit of device-specific parts like initializing of MSIX interrupts or initializing of other interrupts for the sync-based platform. On top of that, we have this platform API and TaPaSCo API. Platform API being very, very low level. You usually should not need to use it if you just want to use TaPaSCo. It's just an abstraction around the device driver to interface with control registers, copy data from the host to the device, stuff like that. And what you're going to use mostly is the TaPaSCo API, which has very high level calls, for example, run a PE of that type with those parameters. And that's where you're attached to. That's the higher layers and applications. So it can be another library, for example, as in the OpenMP case, where this TaPaSCo API was integrated into some compiler-specific libraries. But you can also just use your own C, C++, whatever code to interface with the TaPaSCo API and run your code. And as you can see, you only provide this part, and it doesn't matter on which kind of platform you're running, this always basically stays the same. You might have to recompile, but you don't have to change anything in your user space application to move from Think to a PCIe-based device. So how does it look like? First of all, to scare you off, the C-based approach, which is rather low level. What it does here is we allocate some memory on the device, 1024 bytes. We copy some data from the host to the device. We acquire a PE. We set an argument of that PE, and then we launch the job, get a result, and print that result. It works, but it might not be the best looking, or it's a bit like OpenCL, I guess. It's quite verbose. So what we mainly use is the C++-based API, which is much more concise and sadly a bit cut off. But anyway, what you have to do is TaPaSCo, which will give you the first device it finds. So TaPaSCo also supports multiple devices in the same system. But if you just run it without parameters, you just get the first device. You have any kind of data. For example, we use a standard vector here to store some kind of data. We want a return value from that PE, and then we just run TaPaSCo launch. 10 is the kernel ID. We want a return value, and then we want to copy over the input data just to the device. So we have this specifier make in only just to copy it to the device, but not back after the execution has finished. And running that, it's much more concise and does the same as the C code I showed before. And all those parameter extension is done through template magic to give you this convenient launch function, which handles any kind of parameters. So enough talking. Now you can start playing around with it. What can you expect from the tutorial today? We want to basically show you all steps involved in getting your own bitstream of TaPaSCo. We will build a bitstream on the one hand from HLS for those who like HLS, and on the other hand with your custom HDL, any kind of HDL basically. And we also show you how to build the software part, how to use the API, and how to debug the processing flow if it fails. If it fails for you, everything will work fine, I'm sure. But a disclaimer at the bottom: we use some kind of tricky. As you hopefully already download the Docker image. It's not using real Vivado just to make everything easier. We have used our fake Vivado, which hopefully feels quite real. You can use everything with your own Vivado. Those are just some scripts which replaced the original Vivado commands to make it easier for this tutorial. But if you have your Vivado at home, you can just use that, and it should feel pretty much the same, with a bit more crashing maybe, but that's it. Okay. now we start with just showing around the directory and the Docker setup, and I guess that's where you take over.